Hi, everybody. So first, so I wouldn't run out of time to say thank you for staying so late. Um, okay, this talk I will speak about localization problems. I will start by saying the better we can localize ourselves, the more we can localize ourselves, the better. And then localization would be a great thing. And then I'll change my mind and say that localization is a terrible thing because it really devastates your privacy. And then I'll say something about what we can think about securing your privacy. Anyhow, our model is, at this point, localization is a good thing. We want to tell you where you are the best we could. Think about standard and well-beaten problems like where you are in GPS-less environment, like you're walking in a mall and you don't have GPS signal, like pretending that there is no other technological solutions, or like in rainforest where the canopy creates shelter from GPS points, or cars, vehicles where your GPS is jumped by somebody, it happens. So at this point we have moving users somewhere. I'll get back to this video a bit later when it will be clear then what it is. And users might notice another user moving on, vicinity, short-range communication, Bluetooth, etc. If you think about the mall scenario. And I want to put all this information together and make sense about where are you in this location. Okay, so let's abstract this problem. So I'll think about a scenario at which we are reported essentially two types of events. And each type of events will be stamped, a timestamp. I know exactly where, at which time it happens. First type of event will be the GPS event. Would be the GPS event at which you do get periodically GPS location. Say you are in the canopy, but you just explore to GPS. You have line of sight to a GPS satellite. Or other type of event is two users meet each other, either physically we're in the same point or we're close enough to each other, put some distance of closeness into this relation, this setting, at which we'll say that user AJ, AK, agent user AJ and AK meet, and I know what is a meeting point. And sorry, I do not know what is a meeting point. That's what I'll try to find out, but I do know at which time it happens. Everybody has a synchronized clock. So I will assume here that I know upper bound on each user's velocity. Vj is the velocity of user j. It's the maximum. It's a maximum velocity. As far as I know, maybe the user did not move at all. I do not assume that there was any motion, but I will assume that I know that distinguish walking from running, from driving, etc. Meaning, as obvious as it sounds, that if the same agent was involved in a meeting that happens at time t, later on he was involved in a meeting that happens at time t prime, and Vj is a maximum velocity, then these two meetings happens at distance which is the most, what's the difference between the timestamp times the velocity. Right? Distance time, delta t times velocity will bound the maximum. So roughly speaking, if the one user, say, started to be at the classroom at t equal 1 at 1 a.m., later on he moved to at 2 p.m. he was somewhere at the hotel. Where can he be at 10 minutes after he was in the classroom, but to be just in time, just in a place that will make him be able to get to the hotel where he needs to be in the intersection of these two disks, obviously. Right? this point, it's just intersection of these two disks that we care for. That tells us what is the feasibility region or the point that the user could be. And I will assume, once again, only upper bounds. The problem starts to be extremely harder if you will assume also lower bound on how much he had to move. I will also not make any assumptions here about any stochastic model about his motion. Is he to continue to move in the same time, in the same direction now, or not? I will not say. I'll try to get to the cleanest answer without making any model about the motion patterns. So let's try to characterize the uncertainty, the feasibility region. R at aj of t is where can the agent j be at this particular time, given this we have all the logs of all the meetings. We can have the log either offline, retroactively, or we can have the logs up to this very time t. So you look at this problem for exactly very little time. You realize that if there was a meeting at xj, yj, later on the very same person was meeting x prime, y prime, xk, yk, another meeting point, then I have some bound on the distances. In addition, I have some location anchor points where I did get GPS location. So looking at this problem in very high dimension, in the problem of all the meeting, in the dimension of 2 times all the meeting points, and this is just a convex programming, implying that now if I look at individual agent and ask where he or she was at this time, it's just a convex region in the plane. So let's try to understand what is this region of all the points that it might be. So at some point, we would like to draw all the feasible points, all the feasible region. And I'd like a description of this feasible region. It would be nice if I can describe it as a polygon. Usually I cannot. Maybe it's straight line polygons. Maybe I can represent it as a region with boundaries where every arc is a circular arc. That would be a nice guess, and sometimes I could. So how can I generate the boundary of 3 regions? Well, one clean way to think about it is to think about just a system of ropes that are happening right there. No microphone was hard in this experiment. Basically, I was here, some agent, the red one, was leading the microphone, the top of the microphone at t equal 0. Another one was leading at t equal 1. Each one moved in some certain direction, and to draw, here is where they met at the maximum length that each one moved, and to draw what is the feasible region, to draw the boundary, I'll just pull the intersection point in all 360 directions and generate the boundary of this region. So let's try to analyze what the boundary of this region is. If there are just 2 meeting points, then it's just an intersection of 2. If there is 1 meeting point between 2 users, then it will just be intersection of 2 disks, obviously. If I have a meeting point, like you see right here, two agents met each other after some time, and then one of them continues some distance, and now I'll do this pooling moving experiment. You'll see that the boundary of the region consists of 1 circular arc followed by another circular arc with a much smaller radius followed by another circular arc. So we were proving that motion is always intersection of disks for quite a while, until we figure out that there is a bug in our proof, and it's very tempting to think about that it's always circular arcs, but let's place yet another agent, the white rope that represent the third agent that met the red one right here, made the blue one right here, and now what is the motion that is happening? I was trying to this story. What is the motion that is happening as I move the boundary? And this motion involves having all the vertices of the configuration moving. And each distances in this configuration influence what is the motion that occurs right here. Right? Try to think about it, and I can concatenate and place one, basically, affine transform on top of another one, on top of another one, and each one represents the outer, what will be the final solution. So we don't know what is the boundary of all these creatures. We assume that computing it will be computationally hard. We assume that it has combinatorially only m different pieces. M here is a number of meeting points, a number of events, but each one can be algebraically hard, which we have some thoughts about it as using it for anonymization later on, about how to use it. So if measuring the distance as an Euclidean distance make it so unpleasant to compute, unfeasible as we suspect, then what happens if I just measure the distance using just the L infinity norm? L infinity norm says take the distance on the x coordinate, take the distance, solve all the distances on the x coordinate, or the locations using only the x coordinate, and then use the same distances as on the y coordinate. So what will be, therefore, the location of the meeting points given some sequence of GPS location and some sequence of meetings? You think about it a bit once again. It's a nice undergrad exercise, and you realize that I can just run shortest path in the graph of all GPS. I think that it's the second time, at least in this conference, that we are seeing the power of Dijkstra and it to solve universally a set of problems, one of Dijkstra. So I found out what is the rightmost location where this meeting point might be by finding shortest path to any GPS point that happens to my right. Similarly, I'll find the leftmost location that it could be, meaning it cannot be, the meeting point could not have been anywhere to the left, to the right. Similarly, I'll do it for the upper and lower bounds. This will give me a rectangle, and that's where the meeting point might have been, meaning the employee or the agent has a proof that he has not been in the pub, had the pub be outside this region, unless somebody was violating. And it's cool because one running of Dijkstra solves the problem universally. It solves the problem for all timestamps and for all the agents at the same time. It gives for each one the rectangle where they can all be if they cooperate with each other. So it's nice that there is such a fast algorithm. Now this video makes sense. Basically, all these agents move on a one-dimensional part because they separate x and y. So I can solve the problem separately on x and y. They are sometimes getting GPS location, getting the location. They are sometimes report meeting between each other. And and then I can compute for each one a feasible region. And this feasible region might shrink or increase within time. Once you get GPS location, it's pinpoint to this particular point. Okay. And of course, the paper contains a few other contributions, like, sure, we can back to the L2 norm, Euclidean norm. It's hard to compute it exactly, but it's very easy to approximate it via convex programming. It's easy to approximate in the plane or any small dimension, any convex shape by just picking a few directions and find extreme points. And if you don't like convex programming, you can make it linear programming and approximate it a bit further. So the red region will be what the L infinity measures are, while the blue one will be what the Euclidean distance will say. Of course, you might ask, Usually I cannot move in a straight line. In the mall, I can move either from the left or from the right. Can I still, but with a big island in the middle, can I still find the feasibility region of meeting points? Well, NP hard to solve it, but can have good approximation with pretty wide assumptions. So good news, easy to find. Yep. Running fast. Okay, good news, localization is easy. Bad news, localization is easy. What about your privacy? Your privacy is compromised by you. You're very careful to never share your location with other people, with Post, never used Uber, any location-based services, but your friends are, and sometimes they report about you, sometimes one of the other things represent you, and from your trajectory, it's very easy to know who you are. A lot of literature about how easy it is to de-anonymize the data based on trajectories. Solution, remove points from the reported data or reduce the accuracy, but we cannot do it. We cannot really tell the Uber to meet me somewhere a mile from here. Sometimes it works, sometimes it's unpractical. I don't want to reduce the resolution of the data, and I don't want to remove points. So big picture, let's divide the users into the ones that don't care about the privacy. In the discussion between the co-author of this paper, we refer them as teenagers, the ones that report all the data and report locations. I think that it's okay for me to say big. And the other users which are aware of their privacy and don't share their data. And the ones that don't care still by either having Post or inserting queries or many other means can find out the location of the ones that do care about, or attackers that have access to the Uber/data. So we have some idea about anonymizing the data nevertheless, but first see what's the impact. That's not first, that will be the last thing of this discussion. Let's play with data and see if some users don't report meetings, but don't report their GPS, never. And others do report their GPS. Well, how much does it help us to find the location of the other ones? So we took data of a taxi from Shenzhen. Am I saying it? Taxi data from Shenzhen. I hope that I'm close enough. And it's GPS tracks from taxi cabs from about a huge area, diameter of 42 by 42 kilometers roughly. And we look for the diameter of the region of uncertainty as the way we are measuring privacy. In this sense, it's not differential privacy. It's not one of the other common types. We're trying to say, if I care about my privacy, but somebody says, hey, you are in the East Coast, maybe my privacy is not sacrificed too much. If they say you are right now in UCLA, maybe it's more annoying. So it's what's the diameter of the regions that we are measuring? So let's play with making third of the cabs stop reporting their GPS locations at all. And the other one reports it every 5 minutes. So roughly speaking, here is how we are moving out of the 7,000 cabs, 6,000 cabs. What happened to the region of uncertainty as a number of cabs that are privacy aware and stop reporting their GPS? What happened to the uncertainty data of everybody? Well, it goes from 400 meters up to 700. Not really surprising when you have less and less reported GPS points. But more interestingly, what happened to the feasibility region of just the ones that don't report their GPS, the ones that are the privacy aware? Well, as their numbers grows from 0 to 300, you're getting to 12 kilometers. Well, cabs are moving fast and they are reporting their GPS, even the ones that do only every 5 minutes. But look, still you're getting pretty good accuracy comparing to the overall regions that they might be. You're still getting, well, an accuracy even on the ones that are concerned about the privacy. So it's definitely called for some intervention about more than just stop reporting your GPS. People can still track you based on the side information that is leakage. And running out of time, so good.